We close this section with a digression into some basic notions in topology that, at least for matrix spaces, are familiar from first year analytics and will be used throughout this book. The two concepts we recall here are compactness and continuity. A subset K of X of a matrix space XD is called compact if every sequence in K has a subsequence that converges to some elements of K. Thus, in particular, every compact subset is closed. The notion of compactness carries over to general topological spaces as follows. Let X capital U be a topological space and let K be a subset of X. An open cover of K is a collection of open sets UI. I is in big I, indexed by a set big I, such that K is a subset of the union of UI. I is in big I. The set K is called compact if every open cover K has a finite subcover. That is, if for every open cover UI, I is in big I of K, there exists finitely many indices I1, I2, In. These indices are in big I such that K is a subset of UI, the union of UI1, UI2, UIN. When XD is a matrix space and capital U is equal to capital U, XD is a topology induced by the distance function. The two notions of compactness agree. Thus, for every compact K of X, every sequence in K has a subsequence converging to an element of K if and only if every open cover K has a finite subcover. We emphasize that when K is compact subset of a general topological space, G capital U, it does not follow that K is closed. For example, a finite subset of X is always compact but need not be closed. If U is equal to the empty the set of empty sets and X, then every subset of X is compact, but only the empty set and X itself are closed subsets of X. However, XU is a Hausdorff space. That is, for any two distinct points X, Y are in X, there exists open sets U and V of capital U such that X is in U, Y is in V, and intersection between U and V is the empty set. Then every compact subset of X is closed. Next, recall that a map X from X to Y between two matrix spaces X dx and Y dy is continuous. That is for every X in X and every epsilon positive number, there is a delta positive number such that FB delta X dx is a subset of B epsilon Fx dy if and only if the pre-image of V is a set of every x in X, such that fx is in V of every open subset of Y is an open subset of X. This second notion carries over to general topological spaces. There is a map from X to Y between topological spaces X, UX, and Y, UY is called continuous. If V is in UY, it implies that the pre-image F pair minus 1 B is in UX. It follows directly from the definition that topological spaces from a category in that the composition GF from X to Z of two continuous maps F from X to Y and G from Y to Z between topological space C is again continuous. Another basic observation is that if UF from X to Y is a continuous map between topological space C and K is a compact subset of X, then this image Fk is a compact subset of Y.